Get ready to explore nature's ultimate shape, the sphere. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are wrapping up our discussion about 3D coordinate systems with the best coordinate system of them all, spherical coordinates. The spherical coordinate system is one that is defined by these three coordinates, r, theta, and phi. We have one radial coordinate and two angular coordinates in this system. R is our normal distance from the origin coordinate, and it can take on any value between 0 and infinity. Theta is something called the polar angle, and it's measured down from the z-axis here. It can take on any value between 0 and pi. Now we restrict theta to be between 0 and pi because of the way we define phi. Phi is our azimuthal angle, which is measured from the azimuth, or the x-axis, here. Now phi can take on any value between 0 and 2 pi. So if we had defined theta between 0 and 2 pi, we'd be double counting every point in this space. Sometimes, depending on who you talk to, theta and phi are switched in terms of what they mean, so just make sure that you're on the same page as your teacher or whatever you're working with. Okay, so now that we know these basic definitions, how do these relate to x, y, and z space? As usual, we're gonna extend a line from the origin out to some point on a sphere of radius r, and that point is defined by r, theta, phi. Let's first define x, y, and z in terms of r, theta, and phi. By extending a line out from the origin along the xy plane and then up to that point, r, theta, phi, we can see that we can build a right triangle here. The base of this triangle is also the projection of the hypotenuse onto the xy plane. We can define that length as r sine theta. Now we can define x and y from triangles based off of that projection, which is the hypotenuse of a new right triangle that we draw in the xy plane. That right triangle now incorporates the angle phi. In short, x is equal to r sine theta cosine phi, and y is equal to r sine theta sine phi. Z, fortunately, is the easiest to define. It is simply the adjacent angle to theta in our first triangle here, and so it can be defined as z is equal to r cosine theta. Now what about the other way around? Well, as usual, we can use some right triangle trigonometry and the Pythagorean theorem to define r, theta, and phi in terms of x, y, and z. So for instance, r is going to be defined using the Pythagorean theorem as usual, so it is equal to the square root of x squared plus y squared plus z squared. Theta is here, so it can be defined as the arc cosine of z over r. Now writing that completely in Cartesian coordinates, that would be theta is equal to z over the square root of x squared plus y squared plus z squared. Phi sits here in the xy plane, and so it can be defined as the tangent of phi is equal to y over x. As you can see, phi bears a lot of resemblance to the angular coordinate in the polar coordinate system. Theta, therefore, is the new coordinate that expands us from the polar coordinate system into the spherical coordinate system. Let's take a look at an example. Calculus alert. Like last time, we're gonna be using calculus, so if you haven't seen that before, don't worry, just follow along as best you can. We'll be explaining everything step by step. Let's try a physics problem. Say I have a point charge of 8 microcoulombs at the origin, and I want to find what is the value of the electric field produced by that point charge at a distance of 3 centimeters. Well, for this problem, I'm going to use Gauss's law, which states this: the integral of E dot dA is equal to the charge enclosed over epsilon naught. Vector E is our electric field vector. dA is our infinitesimally small area vector. Q enclosed is the charge enclosed within a spherical shell, and epsilon naught is the permittivity of free space constant. Let's start inside the integral. Vector E dotted with our dA vector can be rewritten as E dA cosine beta, where beta is the angle between E and A. But because E is a radial vector, it points from the origin out towards infinity, and A is also a radial vector. It points away from the surface of the sphere perpendicular to the surface of the sphere. the angle between those two vectors is just 0. So beta is equal to 0, and the cosine of 0 is just 1, so this reduces down to e times dA. So our integral can be rewritten like this. But given the nature of the point charge and the reason that we're using this symmetry in the first place, E is constant everywhere along the surface of this sphere. Therefore, it can be pulled out of the integral. And therefore, our integral reduces to this, E times the integral of dA. Now, what is dA? In Cartesian coordinates, it would be dx dy, or dy dz, or dx dz, depending on our orientation. But in spherical coordinates, we need to figure it out geometrically. If we look at this geometrically, we can see that an infinitesimally small section of area is composed of two arc lengths. One arc length is this, r times an infinitesimally small portion of d theta, the polar angle. The other arc length can be projected onto the xy plane, and it can be found that its length is equal to that projected length times the infinitesimally small azimuthal angle, d phi. Now that projection onto the xy plane, we found that to be r sine theta. So this whole arc length now is r sine theta d phi. Putting that all together, multiplying our two arc lengths together to get one surface area element, dA, we find that that is equal to r squared sine theta d phi. Now we can take this, plug it into our integral, and integrate over the entire sphere. As for our limits of integration, because we're integrating over the entire sphere, we're going to use 0 to pi for theta and 0 to 2 pi for phi. In our case, r is constant. We're looking at a sphere of constant radius, so r squared can pop right out of the integral. The rest of the integral is separable into theta and phi parts, and so we can make this into two multiplicative integrals. One of those integrals is 0 to 2 pi d phi, and the second integral is 0 to pi sine theta d theta. Now these integrals are pretty easy to solve. Our phi integral just becomes 2 pi, and our theta integral becomes this. That just reduces down to 2. Putting this all together and rearranging, solving for E, we get that E is equal to Q over 4 pi epsilon naught r squared, which, if you remember from your physics class, is what we would expect for the electric field of a point charge r distance away. Now let's plug in our values for Q enclosed and R. We know that Q enclosed is equal to 8 times 10 to the negative 6 coulombs, and R is equal to 3 times 10 to the negative 2 meters. Plugging all that in, doing a little bit of math, we find that our final answer for our electric field is 8 times 10 to the 7 newtons per coulomb. Trying to solve with Cartesian coordinates would be pretty difficult, if not impossible by hand, given the way that we define r, theta, and phi. So that's why spherical coordinates can be a whole lot more elegant and simple for solving a problem like this. If you have any questions, leave them in the comments below, along with any suggestions you might have for future episodes of How'd You Get That? Hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. Thanks so much for watching, and I'll see you in the next problem.